Hello everybody. Last time before the midterm exam, we started talking about the multi-view camera geometry. Up to now, whatever we did, we had a single view of the scene. Now we have more than one views of the scene, and in this case we call the setup as stereo setup. And I think I made a small introduction last time. Let's go over very quickly about that introduction. We said that we like to infer depth from images taken at the same time. It is important. Taken at the same time. Okay. Two or more by two or more cameras. Okay, this is called multi-view setup. And human eye, most of the living things eyes are you guys hearing me okay? Did I forget anything?
We can hear you.
Okay. So most of the living things, they have many views, especially the mammals. They have two eyes, and some creatures like the flies and that kind of bugs, they have more than two. Well, they have two main eye groups, but within each eye there are many small light sensitive structures. I don't know what they call it. Okay. But for the mammals, there are two eyes, left and right, and for some of these mammals use two eyes to infer depth. Not all of them, but some of them. Okay, humans definitely we use two eyes to infer depth. We don't get all of our depth information from our two cameras. There are many other things to get this idea from, but getting the depth from two eyes is something we do very frequently, and we rely on that feature. We said that at the beginning of this chapter. Here is an example, the same scene taken with two different cameras at the same time with two different positions, okay, from two different positions. We made a definition last time. Do you remember what disparity was? You guys remember what disparity is?
Coordinates in picture A, where did it go in, the difference between A and B image at the coordinates.
Yeah, exactly. So when I say if the tip of this triangle is at position column number 50 on this image on the left, okay, now look at the same tip point. It is at column number 30, okay, so it is shifted by 20 pixels. So 20 is the disparity of that point, okay, that tip of that triangle, and that disparity will tell us how far the point is from the camera. Okay, if the disparity is large, the point is closer to the camera. If disparity is small, point is far away from the camera. And if we can calculate the disparity of each point in the scene, then I can get a 3D image of the scene, depth image of the scene, like that. Okay, in this image, each pixel corresponds to the disparity of the corresponding point in the real world. Brighter the pixel, higher the disparity, closer to the camera. Darker the pixel, smaller the disparity, away from the camera. Okay, so that's the idea. So at the end of this chapter, we are going to look at these algorithms as long as we can establish the correspondence for each point. As long as we say that, okay, this point here, okay, corresponds to this point here, as long as I can say that, then I can immediately calculate the disparity, and disparity will give us the depth of the point. So in a way, there's stereo processing basically means the correspondence establishment between two images. You might say that we did the correspondence establishment, and in fact we are doing it automatically, but we like to do this in an efficient way. I mean, previously when we did the correspondence establishment, we didn't have any restrictions. Okay, we say that these are two images of the same scene taken from two different positions, but stereo is kind of a little bit different. Stereo introduces lots of constraints, and we like to take the advantage of these constraints. Okay, that's how we started. So as a reminder of the projective perspective projection, we already know that if there is a real world position xyz, when we project it on our image plane, it becomes x over z times f, y over z times f, x and y becomes like that. No problem for us. Basic projective perspective projection for both x and y, and we calculated this from the similarity of the triangles, if you remember, and we talked about this too. Any of these colored dots, they will project to the same point y. Okay, doesn't matter where they are on this line, they will be on this point y. That's why we say that it is not possible to find the depth of a point by looking at it as a single image point y. If you have an image like this, there is a point like that, tell me the depth of this point. You cannot say that, because by looking at a single point, you cannot make this estimation. You could say things about it could be on a line like that. Okay, you could say the depth could be on a line like this, but on this line, which point it is, I don't know. I cannot know that. I need more information. Okay, so single view is usually not enough to do this estimation. You need more information. Okay, one information comes with this case. Okay, take the image of the same scene from a different angle, from the left camera, from the right camera. Okay, I know that all of these points would produce the same P point on the left camera, but on right camera they are different, right? So if I know that this P here corresponds to this blue, then I can definitely draw this red line, and draw this green line, intersect them, and find the depth. Okay, so once you find the correspondence between these two images, finding the xyz of that point P is just making some geometric calculations. Okay, so that's the idea of stereo or multiview geometry. As you see, the corresponding point to this P, it could only happen on this green line here, the line that I'm pointing to. Okay, it cannot be anywhere else. Okay, it cannot be anywhere else. This point or this point cannot be corresponding point of this P, because whatever have caused this P to appear here, it has to be on this line. And if I take a picture of that line is this green line. That's it. Okay, so any point that can correspond to this P could be on this green line, and we call this epipolar constraint. And we are going to look at the geometric explanations of this epipolar constraint. So when we are establishing the correspondence between two images, we don't make a search on the all image. We don't make a search on the whole image. We make a search only on the epipolar line. Good. Okay, so stereo vision, two eyes, we have two eyes, and on the average, the baseline, we call this distance a baseline distance. The baseline distance between two eyes are, on the average, is 63 millimeters. It changes from human to human, of course. Okay, and we see the world from a slightly different perspective. Okay, so let's look at some fun. Okay, fun. For some of you, it may not be that much fun. Okay, some parallax about the difference. The difference between the left eye and right eye is usually called parallax. Parallax. Okay, those two images are different, and that difference is called parallax. And we do lots of experiments with parallax. For example, last week we did that, right? We took out our thumb, and did I lose you? Am I back? Oh yeah, I am back. Yes. Okay, there was a power problem at the building. Okay, so I do this, take my thumb out, and look at my thumb with my left eye and right eye, left eye and right eye, and my thumb, the position of my thumb changes a lot. If thumb is very, very close, like that, very, very close to me, it moves a lot. It moves a lot because the disparity changes for the close by objects. Okay, but disparity is not much for the far away objects. If I'm looking at the far away object, if I'm looking at the mountains at the horizon, their position doesn't change at all from left eye to right eye. Okay, so we did that. We looked at these examples, and I think we were here, and we said that they use this trick to make people believe that they are looking at a 3D world by introducing these kind of glasses. Okay, red filter, okay, and cyan filter. I ask you to buy these kind of glasses for this week's class, but 2 weeks ago we didn't know that there would be the shutdown of the whole country. How many of you have these kind of glasses?
I made it by myself, but it is not very good.
I did the same thing too. See, my glasses are like that. I took a transparent piece of plastic and I painted one side to red, the other side to cyan, but I don't have the cyan color. I painted to blue. Okay, so I am doing this like, but put the red filter over the left eye. Okay, red filter over the left eye. Do this, and I look at the image. The left one works very well, but the right one, since it is not cyan, it's not working very well. But it's kind of, I can see it. Does anybody have these glasses? Anybody have the glasses?
Yeah, I have glass.
Can you look at this, Ongun? Can you look at this picture and tell us if you can see it in 3D?
My glasses is not that blue. They are more like green.
That's a different kind of 3D glass. No, we are not talking. That's electronically controlled kind of stuff. That's polarized. Okay, we are talking about this kind of glasses. These kind of glasses. This one, your left. Okay, your left eye will filter out any red colors. Okay, so it will not see the red parts. Okay, and your right eye will filter out the cyan ones. So one of your eyes will see a different image than the other one. Okay, if I can zoom in here. Okay, this red part will not be seen in one of your eyes, and the cyan one will not be seen by the other eye. Okay, so they will see two different images. Let me do it again. Like this. It kind of works. Yeah, it kind of works with this Mars picture. If I can get it right, I see that these points are closer to me. Okay, let's look at this one. Okay, the closer rocks seemed closer to me. Okay, this is what is happening. I mean, if I look at this picture, okay, if I look at this picture, no, this one, oh, okay, that's why it doesn't work.
I think cyan color, I don't have cyan color, so
I use blue for cyan and it doesn't work very well. But it looks like, I mean, when I look at this picture with the blue color, it starts with a very bright color and it gets darker and darker and darker. The red part doesn't work very well. So for both of your eyes, one part is going to be brighter on the left. For the other one part will be brighter on the right. Okay. So your two eyes are seeing differently, and so your vision center at the back of your head are seeing two different images, and your brain is establishing the correspondence between left and right images that way. Since they are seeing two different images, you kind of see a depth. Okay, you kind of see a depth. That's how it works. Okay, making an anaglyph. Okay, anaglyph is not that difficult. All you have to do is you take the left image, for example, like this one. Okay, you take a left image and right image, and then you clear out one of the RGB channels of this left image and the other RGB channels of the right image, and you put on top of each other, and you produce a single image, and you look at that image using one of these glasses. That's how they do it. Okay. Or maybe it says take a grayscale stereo pair, make them grayscale, and copy the left channel to the red channel, right channel to the green and blue channel, green and blue. Maybe I need to put some green color on it. In that case, it would become cyan. But I don't have the green. Do I have the green color? No, unfortunately, all I have is black. Maybe I can have the green somewhere here. Yeah. No. All I have is blue, green, and red. Blue, black, and red. Okay. So as long as you know how it works, that's fine. Okay. So the question is this: do we sense the depth because we see the world in two different views, left and right eye, or there are other things that gives us the sense of depth? Okay. Up until 1960s, people didn't know the definite answer to this question. I mean, do we get depth from two different views, or we get the depth because we know the scene? Okay. One group of people said that it is the higher level information. For example, when you look at this picture, okay, we have the vanishing points. What's the vanishing point? All the parallel lines, they have to intersect somewhere, okay? And when I look at the images, real world images, I see these vanishing lines, vanishing points, okay, these parallel lines. That's going to give us the perspective. Also, I know that, okay, this person and this person, probably they are at the same height, okay? They are probably 160 centimeters in height, tall, okay? But I see that this person is much smaller on this image. What does that mean? This person is away from the camera, right? That's what I can conclude. Also look at these chairs, okay? This chair is much larger than the chair way at the back. Okay, so this chair is way closer to me. And by looking at these lines, I know that these lines are parallel, and I know that this, and they are going to intersect somewhere. And I know that if I follow this line, okay, to the vanishing point, I know that this building is closer to me than this building. Okay, so I know all of these. And the other thing is the occlusions. Okay, I know that this person is occluding this sign, and that's why I know that this sign has to be away from me than this person. Okay, so by looking at these kind of occlusion stuff, for example, this lamp post is behind this umbrella. Also, all the other tables are behind this table because they are all occluded. By looking at these kind of clues in the image, people said that we know about the depth. In fact, your left eye and right eye doesn't contribute to your left or right, doesn't contribute to your depth perception. That's what they said. But then somebody invented this. Somebody said that, okay, take this random image. This is a random image, okay? It's just a random image. There is no meaning in it. That's why I cannot say that, okay, I cannot say that there is a vanishing point like that, okay? There is no vanishing point. Or I cannot say that these dots here are smaller than these dots here. No, I cannot. They are exactly the same. It's just a random set of points. So what are we going to do with this random set of points? This is what we are going to do. We will take the center part of this image, copy it, move it to the left a little bit. Okay, I move it to the left, this part. Okay, I move it to the left. And this new blank part, okay, doesn't look good. I will fill this in. I will fill this in with new random points. Okay, I will fill this in with new random points. So I have now two images, the original image and the left shifted image. Okay, on the left shifted image I have only the center part is left shifted, the rest of them is exactly the same. So I made an anagram now. Okay, I made them into an anagram. Okay, so when you look at this left image and right image, that doesn't make any difference. They are random dot images with shifted square. And if I do this left image and right image with an analogous, okay, this is what I get. And if I look at this using my glass, okay, like that, I see there is a box floating over the, yeah, I see it. I see there is a box floating over the background. It is closer to me. Okay, if I do that, yes, it is closer to me. So what does that mean? It means that left eye and right eye, by seeing two different images, can give you the sense of depth without using any higher level information. Somebody has invented this in 1960s. Okay, Jules random data experiment, and now people know that with the two eyes we can sense the depth. That doesn't mean that with the two eyes that's the only way to get the depth. Of course, the vanishing points, occlusions, and the comparisons of the size of the objects are also valuable, more valuable than that. But that's going to be one very useful information for us. Left and right eye seeing from different images, different perspectives, will give us the sense of depth. I think I have a question. Yusuf, what is your question?
Before this slide, there was a claim about parallel lines. So we can sense the depth because of the parallel lines. But let's think about that picture is captured by a telecentric lens. We can still sense the depth. So this proves that this is false.
Well, unfortunately, you cannot know. With a telecentric lens, you cannot know which object is closer to you if you don't have a lighting cues or occlusions. Well, I mean, with a telecentric lens, you of course have the occlusions, right?
Mm-hmm.
If you have the occlusions, you can sense the depth. But if you don't have an occlusion, you will not have any way of knowing that which object is closer to you.
Maybe it's about human experience. I mean,
well, if you know the objects, of course, maybe. But I mean, you know that the table cannot be on top of the ball. Ball has to be on top of the table, etc. Okay,
yeah.
Somebody must be holding it. Okay, if I am holding a ball, that okay. Sometimes they do these kind of tricks. You know that people do those kind of tricks when they, for example, look at this. I am holding my head. Am I holding my head? Yeah, I am holding my head. See, you don't believe that, right? If I do that, am I holding my head in my hand? No, okay, because you know that it's just a illusion, or most people even don't believe that it happened. Or if I do this, there is a very large sphere on my head. Can you see it like that? You don't believe that, okay? But with the telecentric lenses, making this kind of stuff is more difficult. But it happens because there is the feature of occlusion. Okay, Doha.
I have a question about last
slide. You mean this one?
yes. Here, the experiment, we shift a little bit to left and then paint something to cyan and something to red. I didn't understand what's happening.
Like the regulars. So this is your left image and right image, right? Make red image your red channel of your RGB image, and make your right image the blue and green channels. Okay, so blue and green channels are this, your red channel is this. If you put them together, you are going to get this image.
Oh, okay, now I understand.
And if you look at this image using this glass, I call this a glass, sorry, okay, and you are going to sense, it's difficult because there are some small areas in my glass that kind of shows me those colors. No, I lost it. I cannot see it anymore. It's too big, maybe like that. No, I lost it. I have to be very careful. Okay, so we know that humans are doing this depth sensing their left and right eyes. Okay. So some other people said that we don't need the glasses if we let people concentrate on these kind of images. Okay, if you look at this image by crossing your eyes and see different things in this image, and you can see the objects in it, and from time to time I can do it, but let's see if I can do it now. Can you guys do it? It needs some, you need some patience. Once you can start doing it, it is always doable, but you need to, you are going to look at it like you are looking at very far away objects. After I get farsighted, I cannot see the nearby objects. After that, I get farsighted, this becomes more difficult for me to see. Making these kind of head movements sometimes works, but anybody got it? Anybody got it? No, I cannot see it now.
I can't see it either.
Well, I mean, you need some free time too, because under stress you can't see it. Some people is very good at it, some people are not. Okay, so
Can farsighted cannot see this?
well, I mean, you need to be looking at a very far away object so that you can cross your eyes, right? You see two different things.
I can never see anything on this pictures.
Well, I used to be like that when I was younger, so for some certain age, it was very easy for me to see it. After I got farsighted, I couldn't see it. But last week I looked at this one, I saw it after a while. Once you start seeing it, you learn it, you remember it, and it is easy for you to see it. Okay, you do this experiment later, okay? What are we expect to see? I think there was certain objects in front of the other. I think there was fish or something like that. I don't remember. I think the same object repeating here and there and there and there and there. I think it was like that. And I don't remember if I see it with my glasses or no glasses. You need to make head movements without, yeah, something is coming here. Okay. Yeah, I see it now. Yeah. No, it's the same thing. It is Saturn. Saturn, I see it. Yeah, it is Saturn. Saturn. Yeah. But it doesn't have its colors, just only the shape. There is this background, and there is this sphere, and there is this belt around it. It is the planet Saturn. So just remember, I looked at this, but again, it is blurry. Let me put my glasses on. Yeah, okay. So much better now. Okay. Now I see the other parts of the sea. Oh, I lost it. So it is not it is not scale variant. When I change the scale, I lost it. Okay, so it is Saturn. Did anybody see it? Maybe I am not. Maybe you are not seeing it as clearly as I am, because you are seeing it from a compressed image through the network. Okay, so I guess nobody see it. I am moving on. So let's look at the geometry of it. That was the fun part of it. Let's look at the mathematics of it. It is even more fun. The same scene, image from two different cameras. This is our simple stereo setup. Very simple. Okay. So I am going to use the same coordinate system. This is our 0, 0, 0. This is the center of projection of the left camera. This is the left camera. This is the right camera. The difference between left and right camera is only this difference in the z x direction, dx. The difference between these two cameras are that's it. Okay, so this is located at 0, 0, 0. This is located at tx 0, 0. Okay, and their focal lengths are the same. Everything is the same. Let's try to see if I have a point in the real world, a point P, large, okay, capital P, capital X, capital Y, capital Z. How would I see this? How would I see this point on my cameras? Okay, so what do? I draw a line like that. So this is small p and another line here. And this is P, let's call this P left and P right. As you see, this small p, okay, the image point P, L and P right, are at different positions on their respective images. Let's try to see how we can write their formulas. For PL, everything is fine. Okay, so for PL, okay, this one, XYZ, it is here and it is there. I know that these 2 points correspond to each other. It is given to me. So XL and XY, this point, XL and XY is F times X over Z, YL is F times Y over Z. So I know their positions for this one. XL and XY. XL and YL. Here, this one. Let's calculate XR and YR. Okay, since I am assuming that this 0, 0, 0 here, I cannot use exactly the same formula for this one because my image, my camera is shifted to the right with this amount, Tx. Okay, maybe I could do this. If I assume that this is 0, 0, 0, how do I assume it? How do I assume that this is 0, 0? If I shift all the real world points to the left by this Tx. So if I take x minus Tx, all of the x's, y and z will not change, then I will be fine, right? Okay, so I am shifting everything in the real world to the left by this amount, by Tx. And I will write the same equation. So it will be XR is going to be F times X minus Tx over Z, and YR is going to be F times Y over Z. That's it. Okay, so I can do this right now. So how do we do the stereo calculations? It was important for us to find the disparity. So I like to know the difference between this point and this point, P, L and PR. Okay, so that's it. But I see that YL and YR are exactly the same. The difference comes from the XL and XR. Okay, let's take the difference. XL minus XR. Okay, that's going to give us the disparity. Okay, I did that already somewhere here. Okay, where did I do that? Okay, if I take the difference between XL and XR, this is XL, okay, and this is XR, this one and this one is the same, of course, okay. What I end up with is this simple formula. Disparity is equal to f times tx over z. Okay, remember this formula all the time. This is the basic stereo formula. Okay, disparity is equal to f times tx over d, or if I replace z and d, z is equal to f times tx over d. So f is fixed for the stereo setup because f is the focal length. Okay, tx is fixed because my cameras are stationary, they are not moving. Z and D depend on each other. If for a given point D is large, then Z is small, right? If D is large, Z is small. If D is small, Z is large. What does that mean? For close by object, D is going to be large. For far away objects, D is going to be small. Okay, that's what we have observed before, and that's what we are saying with this one. So if you have a calibrated camera setup, stereo setup, okay, if you know your focal length, if you know the difference between these two cameras, the baseline, this is called the baseline. Okay, it's called the baseline. If you have a baseline, okay, know your baseline. If you know the D, by multiplying it with f, you will get the z value. D is the disparity. Okay, so once you know the D, the rest is just knowing your setup. You can get your depth from stereo. Okay, any questions?
I have a question. Is f is sorry, focal length is the distance between yes.
Yeah, focal length is the distance between this. This is the principal point, right? This is f.
Okay. Yes. Okay.
And we assume that the focal length of those two cameras are exactly the same.
Hocam o plane'e dik olan uzaklık değil mi?
Yes.
Okay.
I was also something about that. Is it related with the short sight or nearsightedness of the person? Or can it be related?
Selman, can you ask it louder? I couldn't really understand what you said.
Sorry, is it related with the short-sighted or nearsighted of the person that is perceiving it? The F maybe?
Well, no. Well, I mean, if you don't have a very clear picture, of course, establishing the correspondence will not be that easy. But these calculations have nothing to do with the far-sightedness, nearsightedness. No.
Okay.
I mean, to be able to judge the depth of very small objects, of course, you need to have a very sharp image in your head. Sharp image means that you can focus your image very well on your retina. Focusing means that you have a good lens system. If you don't have a good lens system, you get help like that. Okay.
But when we are, I think, short-sighted, the lens is maybe more thick or maybe more thin, so the focal length is maybe more. The focal length of the lens is maybe changing, but is the focal length of the
Well,
lens?
yeah, human stereo is a little bit different than what we are seeing here. I mean, human eye. Let's look at the human eye. That horrible person. Okay, this is not a real person, by the way. You don't look at nearby objects like that, right? You cross your eyes. Just look at my eyes. When I look at the far away things, my eyes become parallel, but when I look at this camera, my eyes are crossed, right? If I do this, my eyes becomes even more crossed. See, I am changing my camera geometry. Our eyes don't look that way.
Okay, I was also gonna ask if we had one eye and was just constantly moving, then we will still pursue depth, right? Because
yeah, sure, yeah. I mean, even with a single eye, of course, you perceive the depth, and two eyes doesn't make any help, doesn't help you at all if the objects are too far away. I mean, how can you know that the tree on a mountain far away is closer than the other trees to you? How would you know that? Your two eyes will not help in that case because the objects are too far away. Okay? Of course, I mean, in that case, even if you have five eyes, doesn't matter because objects are away. But if the objects are close by, the stereo will give you lots of information about the depths of the objects. Okay, do this experiment. Do this experiment. For example, yeah, take a pen and the cap of the pen, two things, right? Okay, and close both of your eyes and don't touch anywhere on your desk. Okay, your elbows are high. Open one of your eyes and try to put this cap on top of this pen. It is not that easy. I mean, maybe I can do it that way, but it is not that easy. How can I can do it? Because this one is too short. Yeah, but with two eyes it is much. Maybe I can do this much better if I do. Yeah. Okay, good. Two pens. Okay, two pens, and I am doing this. I am going to touch one with the other one. Okay, I did it, but it's not that easy. And I think this is apparent for you too. You are looking at my two pens using a single camera of yours. And if I do this, do you think these two will, okay, do you think these two will hit each other if I move them in a straight way? You cannot because you are looking at a single view. But I am looking at it with the two different views. I know that they will touch each other because they are in line. But if I do this, okay, or if I do that, I mean, for this distance, I don't think that you can see the difference between these two. Okay, which one is closer to you? Tell me, red one or the blue one?
Blue one.
Red one.
How many of you will say red one?
I'm saying red one.
Red one, just red one. Raise your hand. Red one, raise your hand. Only one person. Blue one, okay. Blue one, raise your hands. Blue ones, okay. It is a red one. Red one is closer to you.
I saw it when you
Okay, good.
because of that I said.
Yeah, I think they do this experiment like hide the rest of it and do that kind of. How about this one? Which one is closer? Which one is closer? Red. Say red. Whoever. Red is close. Red. Take a vote. Red. Cast your vote for the red. Just two people, one people. How about the blue? Cast your vote for blue. For blue. So I have only 4 people in the class. Okay, I think it was blue. So it is not easy to guess. It is not easy to guess the depth of the object using a single view. But if you have 2 views, it is very easy for me to guess it doing this. Okay, but with a single eye, it is not that easy. Okay, it looks like I'm out of time. Let's take 10 minutes of break. After the break, we will continue with the rest of the discussion. We are doing the fun part, yeah.
Can you open the first slide? You write that big P and little p.
Which one?
I think I missed PR and PL. Yes, here. Okay, thank
Okay, so this is what we have arrived. Z is equal to F times Tx over D. Tx is called baseline. Okay, baseline of the stereo system. As we have seen, for the humans it is like 60 millimeters, about 60 millimeters. But as I said earlier, human stereo is a little bit different than this setup that I showed you, and we are going to look at it later. Okay, so Tx is baseline, F is the focal length. So what we have here is the geometrically explains what we have observed before. Nearby objects have larger disparities, faraway objects have smaller disparities. Okay, so once you have these kind of images next to each other, left and right images, okay, and when you can calculate these kind of disparity maps from these two images, calculate the disparity maps by looking at each disparity point here, by multiplying it with this baseline and dividing it by D, F times baseline times D, F times baseline over D is going to give you the depth of the object, and that's it. Okay, and that's it. Sure, you like to ask a question? Yes.
Well, here we are. We write the coordinate, that difference between two images to the disparity image, but I didn't understand if we are looking for the difference between left and right and left. Yes, right and left. Some points are not mapped in the other the other image.
Yeah, exactly. For example, look at this part. This part here, or should use the red color. Maybe this part doesn't exist on this image, right? It is occluded. Again, look at this one. I don't see this part of the image on the other image, right? These are occlusions. Okay, and stereo cannot help with those kind of situations. Stereo will tell you that I cannot find a correspondence here, so I am not guessing its depth.
Well, while we are doing disparity image, the en sağ alttaki hocam bir cisim var ya, ne cisim olduğunu bilmiyorum onun. Onun bir kısmı diğer resimde gözükmüyor. Şimdi biz
Yeah,
bunu
well,
nasıl
I mean, this is not produced using stereo. This is ground truth. Okay, this was produced using a laser scanner or a projector system.
Okay.
Okay, this is not directly produced from the stereo. But if it was produced from the stereo, then I wouldn't get those positions. But the difficulty is this actually with this stereo processing. You don't know if that part is occluded or not. Okay, most of the time it is very difficult to know that part of the image is occluded. So you report something for that part too, and that would be error. Okay, occlusions are difficult problems for stereo systems. And the other parts are this. How would you establish a correspondence, okay, between this area and the corresponding area in the other image, right? I mean, these are all pure white, right? If I shift my window a little bit to the left or right, it is the same thing. I don't see any difference. Okay, I don't see any difference. The same thing here. Same thing here. Does this point correspond to this point or that point, I don't know, by looking at those local features. So stereo correspondence is not an easy problem. People are still working on it. But once you have the correspondence, finding the depth of the objects is not a difficult thing. Okay? So since these are the basic formulations of our stereo system, we know what stereo is now, more than one view of the same scene. Let's go into more detail and let's look at the more formulations about stereo. Okay, and what do we need about the camera? Okay, this was very simplistic approach just to show you how the stereo works and what is the disparity and etc. What is the problem? What is the simplification with this approach? The approach is we assume that both cameras have exactly the same intrinsic parameters, right? Their f values are same, their pixel sizes are the same, their skew numbers are the same, and etc. And we assume that they are parallel, right? And their y and z directions are x directions are all the same, and they share their 0 0 for their y and z coordinates. These are the assumptions, but these kind of assumptions cannot happen in the real life. We have to be more realistic, and let's try to figure out the more general case of stereo geometry, okay, without making any of these assumptions. So we are going to look at it in a few minutes, but before that, let's look at this image. This is interesting. What did I say? Some of the living things have two eyes. Most of them have two eyes, okay. The interesting ones, at least for us. Some of them have these kind of two eyes. Some of them have these kind of two eyes, okay. What kind of creatures have this kind of two eyes? Okay, they don't have any overlapping field of view. They have their left eye and the right eye on their left side of the head and the right side of the head. Okay, what kind of animals are these? Duck, rabbit, and cow. Okay, so when you catch them, you eat them, right? So these kind of creatures, they try to avoid being eaten. But these kind of creatures, they have overlapping field of view. Left eye and right eye in front of their faces. Their noses are smaller and pointy, okay, and whatever can fit in between these two field of view, okay, they can sense the depth, and these kind of creatures, they try to catch to eat, like owl, cat, dog, eagle, or a human, right? So we eat these, but we try to avoid these. Okay, so they have a reason why they have two eyes to guess the depth, so they can attack and etc. Okay, so this is interesting. Cows and ducks and rabbits, they don't have stereo vision. That doesn't mean that they cannot sense the depth. They sense the depth, of course, by looking at other stuff, but it is more important for them to avoid getting caught by the predators. So they need to see all the way around. Okay, good. So let's go back to our more general formulations of the stereo system, and epipolar geometry will be in the center. Again, I have two cameras, left camera and right camera, and left camera has the image plane pi, right camera has the image plane pi prime. Okay, and left camera has central projection O, right camera has a central projection O prime. There is and as you see, these two cameras are not parallel anymore. Okay, these two These two cameras are not parallel anymore. There is a real world point P, capital P, okay, and the image of this P is a small p on the left image, P prime on the right image. Okay, let's look at this plane, the plane that contains these 3 points, O prime, and P. This is called epipolar plane. Okay, this is called epipolar plane. Okay, epipolar plane is this one. This gray colored plane is the epipolar plane. Okay, and after the epipolar plane we have the conjugated epipolar lines. Epipolar line is this. Look at this point P, the small p. Okay, the real world point that produces P could be this one, this one, this one, this one, this one, this one, this one. Okay, so any of the sorry, maybe I shouldn't start from, okay, any of the points on this red line could produce this P. But if I take a picture of that red line, I would get this line here, right? Okay, so for this P, there is a line in the other image that can contain all the points that can correspond to P. Okay, similarly for this P prime, only these green points can produce this P prime. And if I draw this line P prime, okay, and if I take a picture of it on the left image, I would get this green line here. Okay, so these two lines, green line and the red line, these two lines on the images, are called epipolar lines. Okay, these are epipolar, conjugated epipolar lines. Okay, for small p, there is this red line here. For small p prime, there is this green line here. These are called epipolar lines. Okay, if you draw all the epipolar lines, they all have to pass through this. Okay, these are all epipolar lines, other epipolar lines. They all have to pass through these 2 points, E and E prime. Okay, all the epipolar lines has to go through there. Why? Can you tell me why? Can you tell me why all the epipolar lines has to go through E and E prime?
Can you ask the question again, please?
Tell me why all the epipolar lines have to pass through E and E prime. By the way, these are called epipoles. E and E prime are the epipoles. And all the epipolar lines has to pass through them.
Because of it is baseline. It's on the baseline.
Yeah, because, I mean, look at this epipolar plane. How many epipolar planes are there in this system? How many epipolar planes are there in this system? For each point in the real world, there is an epipolar plane, right?
Here we have one.
For a single point, yes, one. But how many real world points do we have? Infinitely many. So there are infinitely many epipolar planes. Okay, there is an epipolar plane for this point. There is another one, another one, another one, another one. Right? So there are infinitely many epipolar planes on the system, but whatever you do, okay, those epipolar planes has to go through this point O and O prime, okay. And if you are going to draw your epipolar lines with these epipolar planes, what does that mean? One end of those lines has to go through these points E and E prime. Okay, that's why these are special points. These are special points, and they are called epipoles. They are epipoles, and one of them is here, the other one is here. And finally, baseline is our O prime. Baseline is O prime. Okay, this is our baseline. The vector that connects these two camera centers. So I made some definitions: epipolar plane, conjugated epipolar lines, epipoles, and baseline. Okay, so this is the most general stereogeometry that you can have. Okay, if we like to apply these ideas, to the previous example that I showed you, okay, remember this case, okay. Okay, so this Tx is our baseline, right, from O, okay, and this plane here, the one that I'm going to draw, okay, is the epipolar plane. It is the epipolar plane. That's good. What else? And you are going to see that epipolar lines are going to be like these to each other, okay? And epipolar lines are always going to be like parallel to each other. So they need to intersect somewhere. Well, in this case with the cameras, epipolar lines intersect at infinity. Okay, so the epipoles for these kind of systems are at infinity. So using the homogeneous coordinate systems is going to be very useful. Okay, so these kind of parallel cameras, we like them a lot. And we like to make our stereo systems like this so that correspondence establishment is good. And when we look at the images, it is easy to make our searches, etc. And we are going to come to that one. Okay, good. So epipolar constraint, we look at this one. Let's look at this one now. Epipolar constraint, as I said before, this point P or P1 or P2, okay, they all can create this small p on the left image. Okay, any of them could be this p. Okay, but they have different projections on this right image. P prime, P1 prime, and P2 prime. Okay, this L and L prime are conjugated epipolar lines, and this P, if you are going to find the corresponding point on the right image, you are going to check this line only, nowhere else. This is called the epipolar constraint, and this makes our correspondence establishment between two images much easier than we did with the homography or the image stitching, if you remember. Okay, so instead of making a search over all the image, we make search over on a single line. Good. Okay, let's try to write some equations about this epipolar geometry. We know that this O P O prime makes a nice plane, right? So this is what I'm going to do. OP is a vector, right? OP is a vector, right? If I if I cross product OP with O prime, what would I get? OP is a vector, this is a vector, and this is another vector. If I make a cross product of it, of these two vectors, what would I get? I would get another vector, but what is the property of this vector, this new vector? In terms of this plane. Remember, this is a plane. This is a plane. In terms of this nice plane of O prime P, if I cross product these two vectors OP and O prime, what would I get?
Now we have a perpendicular to this plane, a vector that perpendicular to this plane.
Exactly. I have a new vector that is perpendicular to this plane, right? So this angle is 90 degrees. So this is a new vector that is perpendicular to the plane. So any vectors on this plane, if I make a dot product with this vector, okay, if I make a dot product with this vector, it should give me a 0, right? So take any vector on this plane and make a dot product, and it should produce a 0, because any vector on this plane will make a 90-degree angle with this one. So I am going to choose this one, O prime P, another vector. Okay, so I obtain the value of 0 using these three vectors. This is nice, because with these properties of this epipolar geometry, I was able to write a nice equation. Okay, I'm going to use this equation to drive the basic properties of stereogeometry, and I'm going to use those formulations to make calculations later. Okay, that's what we are going to do. So don't forget about this one. What we did was, I took this vector here, okay, I cross producted with this vector. Whatever I get is perpendicular to the epipolar plane. I am going to make a dot product of this vector with this vector here. Okay, and that will give me 0. That's what I'm going to do. Okay, here is the formulations. Or maybe I should put them in the same slide. Yeah, okay. I have OP, O prime, P prime, and O prime. If I take O prime, this one, cross product with O prime, P prime, O prime, and by the way, look at this one. It doesn't do like I did. I took OP, I took O prime, P prime. This one does this. It says that O small p, this one, okay? It takes this vector. Also it takes O prime, P prime, like this one. This is more convenient, because now I am talking about camera coordinates only. P is in this capital P is in the real world coordinates, but O and O prime, small p and small p prime, are in the camera coordinates. So I am using the camera coordinates only. Okay, I forget about the world coordinates. That's what it does. So it says that OP, O prime P prime, and OO prime, they are part of the same plane. If I do this, OO prime cross product O prime P prime times OP is equal to 0. Good. Okay. Now I have two cameras here, and I have two camera coordinate systems. I don't like this because this camera coordinate system is different from this camera coordinate system. I like to express everything with respect to the left camera coordinate system. So what is the difference between left and right? There is a translation between these two, right? There is a translation. Also, there is a rotation. Okay? There is a translation P, translation vector, which is the baseline, and a rotation matrix between these two camera coordinate system. I am going to use these two so that I can express everything on the left camera coordinate system. That's what it happens. Okay. P is this one. That's really what it is. Okay. P is the coordinate of this one in the camera coordinate system. It's a three-dimensional point, P. T is the baseline, which is this one, okay, and P prime is the vector that is expressed in the right camera's coordinate system. If I like to transform this one into the left camera coordinate system, I need to multiply it with R. I don't care about T because I am only interested in the direction of this vector because I am going to do the cross product. So that's it. P times P dot product T cross product R P prime. Okay, this is the baseline. This is the rotation between left and right cameras. Good. Okay, so, and I say that this is going to be 0. So this is interesting. What do we have here? We have 2 points on the image. Remember, these are camera coordinate system, not the image coordinate system. We are talking about millimeters here. We have P and P prime. Also, we have some camera parameters. The translation vector between left and right camera systems, and the rotation matrix between left and right. That's good. That's good. Well, we did not talk about focal length, the alpha ratio, the ratio of the pixel height to pixel width. Okay, we don't have these values. Also, we don't have the skew angle beta. But as we said, we are living in the camera coordinate system now. With the camera coordinate system, we don't talk about the intrinsic camera parameters. They will come later. Okay, so this is good. It talks about the left and right cameras, how we connect them using this baseline vector, and how we do the rotation between these two. Okay, between these two. P and P prime denote the homogeneous image coordinate vectors. No, it is not image. It is camera coordinate vectors. T is the coordinate vector of the translation. R is the rotation matrix such that a free vector with coordinates W in the second coordinate system has coordinates RW in the first one. Okay, good. So what do we have here? If you, this one says that, if you have 2 points corresponding to each other, P and P prime, you have P and you have P prime. Okay, in homogeneous coordinate systems of the camera coordinate system. if I multiply this with this T, which is the baseline, cross product R, okay, T cross product R, you are going to get 0. Looks compact, and it talks about everything. If 2 points correspond to each other, they have to satisfy this. They have to satisfy this. Okay, but we need to make this a little bit more linearly convenient. Okay, T is a vector, this is a matrix. How do you multiply a vector with a matrix using the cross product, right? Okay, this is a vector, right? Three-dimensional vector. This is a matrix, 3 by 3 matrix. How do you cross product two things like that? Well, the answer is this. You multiply this first. Okay, this is going to give you another vector. So I can take the cross product of this one with this one, right? So that would work that way. But we don't like it. We are going to change it a little bit. And I'm going to give you one nice way of making this. We know how to multiply, how to take the cross product of two vectors, right? This is a A1, A2, A3 is vector A. B1, B2, B3 is vector B, right? If I like to take the cross product of these two vectors, this is what I do. You remember this, right? I mean, you take A, this one times this one, and this one times this one. Okay, take the determinant of this part. I and J and K, I and J. Okay. Somebody found this. He said that if you like to do this, you can express this vector A like a matrix. Okay, this vector and this vector. This is a vector, this is a vector. Keep the second as a vector, and I am going to convert the first one to a matrix. And if you do this matrix multiplication, you will do the